Recall from the previous video that we tried multiple solutions. For example, 1 parameter solution, 2 and 3 parameter solution. And as we went and considered higher number of parameters such as x, x square, x cube in our approximate solution, we got closer to our exact solution. Okay, so we can say that with Galerkin method or any method of weighted residuals, the quality of approximate solution u of x depends on the assumption for what the phi's are. So for better convergence, we can consider larger numbers of phi's. For example, we can go for 4 parameter solution or 5 parameter solution. But it is important to keep in mind that since our exact solution contains the term x cubed, and if our assumption for the phi's does not have any x cubed term, we will never get to converge with the exact solution. And this is described more in detail in the section 2.5.2 in the text. Okay. Further, if there is a change in essential boundary condition, our approximation function will need to change, will need to be modified. Okay. Further, satisfying the essential boundary conditions becomes cumbersome as you go in the domain that is more complex, or if you go in a higher dimension such as 2 or 3 dimension domains. And that is described more in detail in the section 2.5.1 in the textbook. In order to get a solution, an approximate solution that is close to the exact solution, we will often consider more complex functions phi's for our approximate solution, and those are often harder to integrate. Due to such issues noted here, it is very hard to generalize the process of solving, the process of getting an approximate solution for our partial differential equation. And that is when the finite element analysis comes into picture. Using finite element analysis, we can resolve these issues by assuming a domain discretized into tiny little domains and solving the weak form over each such domain. So in the next video, we'll focus on describing what a finite element is and deriving equations for finite element method based on the Galerkin weak form.